Good afternoon, everyone, and welcome to today's CECAN webinar. My name is Lisa Fletcher, and I'm one of the two part-time CECAN Centre managers. For those of you who are new to CECAN, CECAN stands for the Centre for the Evaluation of Complexity Across the Nexus. For the past 3 years, we have been transforming the practice of policy evaluation across the food, energy, water, and environmental domains to make it fit for a complex world. We have achieved this through pioneering, testing and promoting innovative policy evaluation approaches with UK government departments. To find out more about our work, please visit our website at www.cecan.ac.uk. Today's webinar focuses on the trophic analysis of directed networks. We are delighted to present Professor Robert MacKay from the University of Warwick. Robert is going to speak to us for around 45 minutes, and then we'll have some time to answer questions at the end. Please submit your questions at any point using the question and answer box only, which you should be able to see on the Zoom webinar control panel. The webinar is being recorded and will shortly be made available on our CECAN website. I will now hand you over to Robert for the presentation.
Hello, everybody. Let me just get my video on as well. So I hope I'm audible and visible. Okay, it's a pleasure to be invited to give this webinar. I'm going to speak about a method which may sound rather obscure with the title we've given, but I think could be valuable for evaluation of policy and many other domains, in fact, but I'll concentrate on the evaluation of policy side. So this is joint work with Basil Sanson and Sam Johnson, and I'm particularly grateful to Basil for help with putting the slides together for today. It is supported by the ESRC, by the Instability Hub of the Rebuilding Macroeconomics Programme, which is managed by the National Institute of Economic and Social Research. And I'm going to concentrate here on the potential relevance of trophic analysis to systems maps and related themes for evaluation of complex systems. So we'll begin with an example, which is a CECAN example. Alex Penn and the team put together a guide on participatory systems mapping. And this is an illustration of systems mapping from one project that she and others were involved in. BBE at the center stands for bio-based economy. And this is to look at the causal relationships between relevant factors for bio-based economy energy. And the idea of a systems map is we indicate causal relations by arrows. And here we have thick arrows if it's a strong cause and thinner ones if it's weaker. And also in this particular diagram, there's a sign attached which says whether the increase in something to do with this factor increases or decreases this factor. That's a feature that we're not addressing in our current work, but obviously is an important one to think about. So that's an example of a systems map. I hope it makes clear what it is. And what we do is trophic analysis, and the effect of that is shown on the next slide. So what we've done here is to redraw that network where horizontal position is now what we call trophic level. So we start with the things which have no incoming arrows, like international instability here. And we end with things that have no outgoing arrows, like land availability here, community acceptance. And we arrange things in between in such a way that we try to make each edge move by 1 unit to the right. But of course, there are some incompatibilities. Things like, say, this loop, we can go from energy to byproducts to competitiveness and back. So it's obviously impossible to make the level increase by 1 along each of these 3 edges. And our method produces what we consider to be a most sensible allocation of levels that's compatible with this goal. Another thing that our method does is to quantify what we call incoherence of the flow of influence. So this is the extent to which it's not possible to make all the levels change by exactly +1. And we have a quantification that is on a scale of 0 to 1. In this example, the incoherence comes out to be 0.6. So that's representing the fact that it's quite a long way from the simple picture of an acyclic influence network. And just to emphasize here, our method can take into account edge weights. Here we interpreted strong as 1, medium as 2/3, weak as 1/2. But if you have more appropriate quantitative measures of edge weight, then of course you can put that in as well. So that's one example. And what we hope is that this stretching things out by trophic level leads to a better understanding of the system's map. So I've said a bit of this already, but how does trophic analysis work? It tries to assign levels to the nodes. We've plotted horizontally here to be consistent with how systems maps are sometimes presented. So the level increases by 1 along each edge. And more precisely, we let Wij be the weight of the edge from I to j. And we minimize the sum over edges, weighted sum of the edges, of height difference -1 squared over possible choices of the heights. And then we let the incoherence, which we call F0, it's not a particularly good name, but be the minimizing value of this sum. And we get a unique solution H, modulo adding arbitrary constants in each so-called weakly connected component. We could obviously add the same constant to all the H's and it wouldn't change this sum. But that's trivial, it's just setting a 0 of the level. And furthermore, the solution of this minimization problem is given by solving a linear system, certain matrix L, which is symmetrized weighted graph Laplacian, for those who are familiar with that. I didn't write its formula here. Acting on the vector of heights is equal to what we call the imbalance vector for the influences. Imbalance vector at node J is the sum of the incoming weights minus the sum of the outgoing weights. So it's saying how much influence is, how much more influence is coming into the node than is going out of the node. And that turns out to be the appropriate right-hand side to put here. I should mention at this point that there are other versions of trophic analysis. The original one was introduced by Levine a long time ago, must be 50 or more years ago. And but more recently, there have been some others. Some economists have produced the same thing as Levine. Schwabe, who's a PhD student at the University of Warwick, with his supervisors, has produced a slight alternative of what we have here. And there's an equivalent formulation that we learned about by a Japanese group led by Iatomi. So that's just to put it in context. But I'm concentrating on our version because we believe it's the best, at least for many purposes. So let's do another example. This is another one from CECAN, which was led by Pete Barbrook-Johnson, and it's taken from CECAN Note 17 from April of this year. and it was a project done for Bayes on the renewable heat incentive system. So the policy connections. So what are the important factors in renewable heat incentive policy implementation? And what are the causal links? So they came up with a systems map that looks like this. And they've organized things in 3 columns. There's a left part called policy, there's a middle part called deployment and business case, and there's a right part called outputs. So in some sense, this is approaching the trophic layout that I already showed for Alex's example. But we can still ask what happens if we do our trophic layout. And the answer is here. So we've used the same color code, so you can see all those blue things which were called policy in the policy column. They've actually got a bit spread out here. So there's some bits of policy that are, well, the renewable heat incentive policy, of course, causes various sub-clauses of the policy. And the outputs, which were in yellow, indeed are principally over here on the right. But we see a lot more structure going on here than was in Pete's original diagram. What we notice about this one is actually there aren't many loops, and actually it's quite close to being coherent. So the incoherence that we compute is 0.2. If you like, the coherence is 0.8. And that corresponds to the fact that mostly this is edges increasing by +1 each time we go along. There's some in the middle way here where it gets a bit mixed up. That's why it's got a bit of incoherence. So what does this incoherence measure? Because it's something we believe is particularly important. Let's do on 3 or 4 simple networks or motifs. So suppose we just had a network of causes and influences where A1 and A2 feed into B and B affects C1 and C2. Then this one is perfectly coherent, and indeed its incoherence comes out to be 0. Here we have something that is still acyclic, but is not perfectly coherent in our sense, because A influences C, but also indirectly via B. And because our method is trying to make the level change by +1 along each edge, that's impossible here, because we'd have to have 1 + 1 = 1. And so it chooses levels that are not quite 1 apart in this example. I think it's 2/3 it chooses, 2/3 from A to B, B to C, and 4/3 from A to C. And the incoherence then works out to be 1/9. Here's an example where we have a loop, a cycle, as well as quite a lot of direct causal links. And in this case, in order to cope with this D to E in particular cause, whereas E is supposed to be close to A and D is supposed to be close to G, then we end up with a bigger incoherence, 2/5 in this example. These examples we put weight 1 on every edge. You could obviously change the weights, but just for illustration, that's what we've done. And the extreme case here I've drawn where everything is actually at the same level, because there's as much influence coming into each node as is going out of it. So here, B influences A with weight 1 and A influences B with weight 1. So that's the smallest completely incoherent network that we could draw. I could draw with more nodes, but then they'd all have to be on the same level, so it gets a bit difficult to see. So these networks, I should mention, were drawn using a program called Prism, and thanks to Nigel Gilbert, and people who've put it together. So the answer to this question, what does incoherence measure, is it measures the failure of level differences to all be +1. Some people call it circularity, in particular the Japanese group. And this has a lot of sense to it. So in particular, existence of a cycle forces the incoherence to be positive. It's impossible to be perfectly coherent and have a cycle. As I already explained, the levels can't increase by +1 along every edge in the cycle. Furthermore, if the incoherence is 1, so meaning that it's perfectly incoherent, then actually you can prove that every edge is in a cycle. So there must be lots of cycles. But in between, you can't completely deduce whether it's got cycles or not. Nonetheless, we have some interesting work. I'm calling it a conjecture here. It's got some backup, but it's not yet on the level of proved result, I would say. That a certain quantification we call rho sub s of cyclicity, so something to do with how many cycles the network has, behaves typically like this as a function of the incoherence. And rather than the formula, it's easier just to look at this graph. It's the blue curve. Incoherence along the bottom going from 0 to 1, and this rho s going from 0 to 1 on the vertical. So it's a non-trivial relationship. Starts rather slow and then it speeds up. And what Sam Johnson has done here is to compare with some empirical networks, not systems maps in this case, but with food webs from ecology, genetic networks, metabolic networks, neural networks, language networks, trade networks, and some social networks. And these results, empirical results, are plotted here. And you can see there's a fairly reasonable lineup with our conjecture. So this is an alternative interpretation of incoherence. It's some measure, or it's related to measure of cyclicity, amount of cycles, even though, as I've said, positive incoherence doesn't necessarily imply there are any cycles. It could just be feed forward, things like this. So let's do a few more examples to get the idea, and in particular to introduce some alternative technology. Systems map seems to be the main word we use in CECAN for these things, but other groups use all sorts of different words. So one is fuzzy cognitive map, and this was for a stakeholder workshop in Bolivia. And this is the way they presented it. So it's to do with deforestation. And we've presented it using trophic level horizontally, and this is what we get. And we see that this one is actually very coherent. The incoherence is nearly 0. And you can see basically the horizontal position increases by exactly +1 actually along this chain, and then almost +1 here. And we've drawn in pink the ones which have no incoming causes, so we call them exogenous. And we've drawn in yellow the outcomes, the ones that don't cause anything, at least in the scope of this diagram. And the green ones are in between. So an interesting thing here is that the external causes can come in at various levels. And our method doesn't force them all to start at 0, in contrast to some others. And we think this can be an advantage. Okay, then one other example, which is for an article called Garden Instead of Concrete. So it's to do with city space and cycling and green space. And in this article, they're particularly interested in identifying cycles. So you can see these things like B2, there's a cycle there. Sorry, it's a bit ambiguous. Bicycle and cycle are not supposed to be the same thing. So here we have an example with lots of cycles. And when we plot it, indeed, we get quite a large incoherence. So remember, incoherence can be called cyclicity. Again, we see there are the green nodes in this case, which have no incoming causes, at least in the scope here, which are affecting everything else. As I said, there are various alternative terminologies. So another terminology that seems to me, though, I'd be interested in experts' opinions, but to be equivalent to systems mapping is influence mapping. So for example, this is quite common in company management structure. So here we would have someone who is in charge basically and influences strongly or weakly various other parts of the organization. But there are still some cycles, for example, here and here. And this under the name influence mapping, actually, there's a huge industry, with various companies selling tools. So this article by Mulder gives a survey. But none of them, as far as I'm aware, deduce trophic levels. You can see in this picture, of course, they've arranged things roughly in trophic levels, because the trophic level would now go up by 1 every time you go down in this picture, roughly. It's not exactly that, because this connection does a jump. And of course, you have to deal with these loops. Under the term influence mapping, though actually there are some in CECAN, particularly Stuart Astill, who use that. I think he makes some distinctions, but he ran a online training under CECAN Continuous Professional Development Program. And the difference, I would say, at least from what I understand here, is that they put Bayesian belief propagation on the networks. And I think this requires them to be acyclic. They shouldn't have any cycles at the beginning, because it's not obvious how to put a Bayesian belief network on a graph that has any cycles. Another name for these systems mapping is causal loop diagram. And here's one from Wikipedia for some life insurance company. Again, they're particularly interested in cycles, as of course causal loop would suggest. That's the feature they really want to concentrate on, the fact that there are cycles. Another name for these systems mappings is outcome pathways. And this is a particularly common name in the context of what are called theories of change. So here's an example again from Wikipedia. It's a child welfare topic. These outcome pathways in theories of change are often acyclic. You can see in this case there are no cycles. You start from here, you go to there or there, and then you go up here or you go up here. And you never have the chance of coming back to anywhere. So outcome pathways are also known as results chains. So chain, of course, strongly suggests that there are no cycles. Doesn't mean that it's just a single chain. Here you can see it's a branching chain, but it's acyclic. Or sometimes it's called a logic chart. So as I mentioned, this one is acyclic, but actually it's even stronger than that. It's perfectly coherent. You can see we can make the levels increase by +1 along every edge consistently. You might think that this looks as if it doesn't work, but actually this one goes to here and to here. So actually you can put +1, +1, +1, +1, +1, +1, and get the same by going the other way around. That's maybe a fluke for this particular example, but I think the restriction to acyclic diagrams is unnecessary. And indeed, a lot of what we're calling complexity, I think, results from the existence of cycles. So there can be cycles of cause. A subsidiary theme in theories of change is contribution analysis. So I should say I'm not expert on all of this. I've learned a lot from colleagues in CECAN, and I'm just trying to put what I'm talking about in context. But contribution analysis attempts to quantify the influence of a decision on an outcome. And so in principle, it could give some quantification of the weight of the edges in a diagram like this. Well, I've mentioned that our method assigns some amount of incoherence, even if there aren't any cycles. And you might say, well, actually, what we really want to distinguish between is acyclic networks of cause and ones with possible cycles, and we'd like a measure of how many cycles there are. So there are measures like that, particularly in computer science. There's something called agony. So you think about the minimum number of edges you'd have to delete to kill all the cycles, and then you divide that by the total number of edges. And so our method, that wasn't our goal, at least at the beginning, but it could still be important to think about what happens if we modify this choice of target level difference being +1. So as I explained at the beginning, the goal is to try and make the level change by 1 along each edge. And if you have a feed-forward loop like this, then that's impossible. But suppose we made our targets be 1/2, 1/2, and 1. Then, of course, it's perfectly possible. We can achieve exactly that. And it might be that actually we do strongly think of B as some intermediate between A and C. And so we would like to make these target height differences, level differences be 1/2 instead of 1. An example that we started with in this vein is in production networks. So it might be that you have one company that actually has two subunits, one of which supplies the other. And you might not want to say that they're trying to make them distance 1 apart because they're part of the same company. You might want to make them much smaller distance apart. So let's explore this idea that we should not necessarily force all the target level differences to be +1. So we could specify target differences based on some expert opinion on how far apart we think they ought to be. We'll call these tau mn for the distance from m to n, the level change. And then the levels h, what we want to do is to minimize the weighted sum of squares of the level change minus the target level change. And I've normalized by this sum. Minimize that over the choice of levels. So again, there's the ambiguity. You could shift the origin of levels. It doesn't change anything. But apart from that, it's equivalent to, again, solving a linear system. L is the graph Laplacian again, acting on H, but is equal to a different V. So our imbalance vector becomes this version that is weighted by the targets. So we have again here the incoming weight of edges, but times their targets, minus the sum of the outgoing weights times their target height level differences. So this is a perfectly possible generalization if you have reason to make the tau mn's different. So a direction that we're thinking about is maybe you could allow the target height differences to choose themselves. We could minimize this expression over the taus as well as h, or something like that. So of course it collapses rather, potentially it collapses rather trivially. We need something to try and stop the taus all going to 0. Maybe this denominator is good enough, but the goal would be to leave incoherence, so the minimizing value of this, to come only from cycles, not from feed-forward motifs. So that's a project that we have for the future, which I think could be interesting. But something we've done in the meantime is, as an extreme case of specifying target level differences, we've made a method to assign strengths to teams, thinking in the football sports context, based on a set of pairwise comparisons that's not necessarily complete. And the motivation for this, of course, was the suspended Premier League because of COVID. And the example I'll present instead of the Premier League is the Women's Super League, because the Premier League actually did get restarted and completed. But the point is that you can still infer relative strengths of teams from incomplete pairwise comparisons, as long as there are enough to connect them all to each other. So here's the table as the Women's Super League ended in March. Blue means a home win, and red means an away win, and yellow means a draw. And what we did is to minimize weights. So the weight is just actually the number of matches played, which in this case was 1 home or 0 home, and 1 away or 0 away. So it's rather trivial, the weights. The important thing is we put the goal difference for the score as our target. So we have a target of the goal difference. And then we're choosing levels, which here I'm calling strengths, big S. So the level difference tries to match the goal difference that was actually achieved. And actually a bit more subtle, we allow the target to depend on which team was playing home and which was away, right? So there's a home advantage, so in general. So we allowed the method to choose a home advantage as well. So that's part of variability in the target. The target, if you like, was the actual goal difference minus the adjustable home advantage. And when we do this, well, first without the home advantage thing, then we get this. So I've put the strengths vertically instead of horizontally. That's how in most of our work we think about it. I just did horizontal because that seems to be, like in Pete's example, more common in the systems mapping, or at least fits better with the intuitions in the systems mapping world. So here we have strengths, Chelsea women's at the top and Bristol at the bottom. And then if we include the adjustable home advantage, the minimizing value is about 0.38. It actually makes very little change. There's a bit of movement here, and Arsenal ends up above Man City slightly here. In the end, the Women's Super League decided the outcome on points per game, which I consider not particularly fair, because a lot depends on which games you had coming up, whether it was against relatively easy or difficult opponents. And also, that didn't take into account the numbers of home and away games that you played. But anyway, that's what they chose. So this final column shows the points per game, inferred strengths. So you can see at the top it corresponds reasonably well, but at the bottom it has a big effect. So Liverpool ended up right at the bottom. And of course, you know, the real Women's Super League is played by points, is determined by points, not by goal differences. So of course the points per game has that advantage, that it was using points, not goal differences. But still, I think there can be contexts in which it's sensible to use a quantitative measure of relative strength in a pairwise comparison. And then this method would be useful. One thing we didn't do, and I realized only in preparing this talk, is we didn't compute the incoherence of the results. Right? So I haven't drawn the edges in this network, but in principle, there's an edge corresponding to each match that was played in this table. And the question is, do all the edges go up by roughly +1 or not? So yeah, I should go back and compute that. I have all the data, so it should be easy, but it'd be interesting to do. Good, so I think we're near the end now. I'd like to pose questions about what do we want systems maps to achieve, and in this includes all the variant names, influence maps, cognitive maps, etc. So one of the things that I've learned from my CECAN colleagues is that an important goal of making systems map is actually to involve the stakeholders. So even if there isn't an end use for the systems map, it's a way of inviting all the stakeholders to take part and to specify what they think is important. And that means, in particular, that if one did come up with an end use for the systems map, then we've already got buy-in, assuming the participants, agreed more or less with the outcome. We got some buy-in from the stakeholders. So that's one thing. Another that I think is important, and I've hinted about, is that making a systems map displays the complexity of most policy environments. So the existence of cycles in these diagrams is something that you might not have anticipated at the beginning, and yet it's basically agreed by the participants that there are cycles, and so one has to think about what the consequences of these cycles are. I think that's a very important value in making the systems map. Now you can go further with some quantification. Contribution analysis in particular attributes the quantification of cause to interventions. But my understanding is it's usually based on an acyclic systems map. So perhaps Barbara or others can fill me in on this, but I'm not aware of how to do contribution analysis if we allow cycles. So the thing that I'm suggesting here as a potentially useful additional method of analysis is what we're calling trophic analysis. And what it does is to lay out a preferred horizontal coordinate, indicating, in some sense, how far along the flow of influence is a given factor. Sorry, that's my phone going, but it will stop in a minute, I guess. It also quantifies the extent to which the network fails to be perfectly coherent, with factors arranged in layers. So these layers were vertical in the diagrams we indicated, and level differences being 1, right? So that would be the perfectly coherence case. And this is what a lot of naive diagrams for management organizations and production networks and various other things assume, but in reality, they're not perfectly coherent in general. But the incoherence that we've developed has some potential defects. It confounds cycles with feed-forward motifs. So you can't deduce from incoherence that you've got cycles. And then another thing is we haven't yet taken signs of edges. There's the sign of the influence into account, because the sign is something that assumes one-dimensionality of each factor. Otherwise, you'd need something more complicated representation of the strength or the sign of an edge. You need a matrix, really, at least. But this is another thing that needs addressing. Of course, you could say in the football case, in some sense, we took signs of edges into account because there was the sign of the goal difference. So the football case, then we arranged things where the home team was first and the away team second. So there's a sign to those target height level differences. But that's maybe rather a special case. So I think I'd like to close on this question of what we want systems maps to achieve. And I'll just put a final one with some references. There's a, a paper that came out just a couple of weeks ago on how directed is a directed network. So this puts out our formulation of trophic analysis and comparisons with previous methods, and also some consequences. We started this work prompted by the question of stability of economies, in particular stability of supply networks. And so what we wanted to see is if there was a connection between the trophic incoherence or otherwise of a production network and stability of some aspect of it. So we don't have a definitive conclusion, but the paper gives a few starting points, and we're working on it more. And then the application to incomplete football seasons is in this members magazine of the Institute of Mathematics and Applications. Okay, well, thanks very much for your attention, and I'll be very happy to receive questions. So I'll put them in the Q&A, and what we're going to do is I'll have a look at the Q&A, and I'll get Lisa to take over displaying my slides in case we want to refer to them, so that I can look at the Q&A. Okay, so shall I start looking at the questions? So first one is from Steve Powell. How does the layout using trophic levels differ from popular existing approaches like Sugiyama, which is used by iGraph, or DOT as used by GraphViz? Do they actually already use trophic levels as we define them? So I'm not familiar with either of these. It is perfectly possible that someone has found it before. Indeed, there's a paper we discovered from 2002 in which some computer scientists proposed the same notion of trophic level as us. And they did this in the context of graphical representation of directed networks. So I don't know how far that has been taken up. One thing that they didn't focus on, though, is this notion of incoherence, which is subsidiary quantity, which we feel has independent interest. So, but I'd be very interested in following up with companies who make visualization tools. I keep my eye on some of them, like Cambridge Intelligence, for example, does quite a lot of these visualization tools. And at some stage, I'd like to talk with them or others and to see whether they think trophic analysis might be a useful thing to add. I have, of course, already been talking with Nigel Gilbert about this in the context of PRISM. So I hope that gives some answer. I'm afraid it's incomplete, but it's definitely an important direction to explore further. And if any of you do know some tool that already uses trophic analysis, then I'd be very interested to see. Next question from Pete Barbrook-Johnson. Is there a reason I use the phrasing fails to be perfectly coherent? The negative framing suggests maps should be coherent, but this is not the case. If we were to use this language with stakeholders, it would cause a lot of confusion. I think you're right here, Pete. We're just inheriting the term trophic incoherence from previous work, principally in the ecological sphere, where the ecologists imagined at the beginning that a food web would be perfectly coherent in the sense of having a level 0 of plants and a level 1 of herbivores and a level 2 of carnivores and maybe a bit more a few other levels. But in reality, every food web that is real food web that is plotted isn't perfectly coherent, and so for them that's the sort of shock, maybe is the wrong word. Maybe they knew it wasn't going to be perfectly coherent, and of course they've known this now for many years. But that's the reason for our use of the word coherent and incoherent. But I agree it's not particularly helpful. So an alternative is to use this word circularity from Iatomi et al. Instead of incoherence, and that conveys to some extent what's really at stake. On the other hand, it's not quite exact, because, as I've said, feed-forward networks are also contributors to incoherence. So, sorry again about my phone. I should have thought of turning it off at the beginning. But, it's made me lose the thread. But incoherence is not necessarily, doesn't imply cycles. So that's why the use of the word circularity is a bit worrying to me. But at least it has the advantage that it's not a negative. So we do need to play with terminology and perhaps come up with the right word. And then Pete Barbrook-Johnson again. For what it's worth, to me, the term systems mapping is an umbrella term which can apply many different methods which represent systems with nodes and edges. What the edges and nodes represent and what analysis is done on them differs between each method. So here we have FCM, BBN, SD, rich pictures, etc., etc. So probably it's best if maybe we could invite Pete to amplify on this.
I'll have to unmute him. Just hold on.
Thanks.
Hold on. I don't think I can. It's not letting me. We can chat with him. Sorry, Robert. In the original setup for this, Gail's obviously not allowed participants to speak.
Okay. Well, so
I'm just trying to see if I can. There's no other workaround, is there?
You can probably make him a co-host.
Yes.
And then.
I don't think I can. Now we're live.
Okay.
I'll try.
So yeah, there's lots here that definitely I need filling in on. I'd be pleased if there are connections or differences. But so I think among the acronyms that Pete has given, I recognize BBN is probably Bayesian Belief Network, which I've commented on. But as I've said, as far as I'm aware, they're formulated for acyclic networks. Okay, any other questions? There's the, I see there are more now in the Q&A. Yes, good. Steve Powell again. Would you still call one of these maps a systems map if it didn't happen to have a loop cycle? What would make it a systems map as opposed to just a common or garden causal map? I'm happy to call them a systems map even if it doesn't have a cycle. But one could call it a causal map. It's just it wouldn't have causal loops. But if you have a nice system like that, some people call them linear, which I always find terribly confusing, but where there are no cycles, I prefer to say acyclic, then it's much easier to analyze. For example, you could propagate Bayesian belief. And then Steve again, seems to me that a system would be something quite specific, and all of what you say applies willy-nilly to general causal maps which don't have loops or any other specific systems properties. So I'd say yes, in a sense. Our method can be applied to any directed network. That's some part of what we think is the power of it. So a problem with the old version of Levene for trophic analysis is it required you to have basal nodes, ones with no inputs. And many networks, particularly in economics, have no basal nodes. So this means you can't get started with Levene's notion. And we developed a notion precisely to deal with that problem. And we envisage our trophic analysis being relevant to a huge range of types of system, as we've illustrated already, genetic, neural, language translation, financial networks.
Okay, I think that's all the questions that you've gone through there, Robert. Is that right?
Yeah, I'm just looking through the chat in case there was something.
There was one, and I've emailed it to you. Yeah, again, it was from Steve.
Oh, yeah, sorry, I haven't looked at my email yet. Yeah, we said we'd do that. All right, let me move things off the top. Yes, that was the original question from Steve. Okay, good.
Well, great. Thank you, Robert, for today's webinar. Very interesting. That brings us to the end of the webinar today. As I mentioned earlier, we'll be adding the recording to our website in the coming days. Thank you all for attending, and thank you, Robert, for hosting the webinar. Goodbye, everyone. Hope you have a lovely afternoon.
Bye.
Bye.